Hi, everyone. My name is Brandon Rodriguez. Thanks so much for joining today. I'm here representing the Education Department at NASA's Jet Propulsion Laboratory in Pasadena, California. I'm really excited to have you guys here this month to talk about exploring exoplanets, these uh, planets that orbit stars other than our own. So when it comes to looking deep into space and trying to understand a neighborhood other than our solar system, this can take some pretty intense technology. And we're very, very lucky today to be joined by Vanessa Bailey, who is going to walk us through some of the research that we're doing at NASA to understand just how many of these worlds exist in our universe. So very quickly, I'll let you guys know that we're very, very thrilled to have our subject matter expert here to kind of talk us through some of this cutting edge research. After her presentation, we'll take some questions from you in the audience. And then I'll close out by talking a little bit about some of the education resources we have. So if you've enjoyed this and you want to learn more, or you're a teacher or a parent and you want to share this with your students or your children, there are so many ways to engage with this and take it a little bit further. So without further ado, let me turn it over to Vanessa, and thanks so much for joining us.
Oh, thanks so much for that great introduction, Brandon. And I'm really excited for the invitation to be here to talk to all of you about exoplanets, something that I'm just passionate about and so excited to be at JPL researching. So I'll be talking to you a bit today about the history of planetary discovery, exoplanetary discovery, talk a little bit about some of the ways that astronomers find exoplanets, and then dive more specifically into one of those detection techniques called direct imaging, and talk to you more about this instrument called the Nancy Grace Roman Space Telescope Coronagraph instrument. Whew, that's a mouthful, but we'll get there. That will directly image exoplanets just a few years from now. So if I think about the timeline of planetary discovery and exoplanetary discovery, it's simultaneously some of the oldest science and some of the newest science. And if you think back to ancient times, 1,000 years BC, the first scientists were people who looked up at the night sky, who monitored it from day to day, from night to night, from season to season, and they saw these 5 objects that seemed to be moving relative to all the other stars. And those were the naked eye planets: Mercury, Venus, Mars, Jupiter, and Saturn. So some of our earliest scientists were discovering planets thousands of years ago. And on slide 3, as we progress significantly farther through time, 1600s, 1700s, 1800s, we're building better and better technology. We're with the advent of telescopes, we can now see the moons around Jupiter and Saturn. With the advent of more sophisticated mathematics to describe those orbits, we realize, in fact, that not all the planets are orbiting around Earth. We're all the planets orbiting around the sun, and Earth becomes a planet for the first time. Then, as we develop the mathematics even further, we can predict where planets should be in their orbits over time, can notice perturbations and actually predict the existence of Neptune based on perturbations of Uranus's orbit. We look there, astronomers look there, discover Neptune. So it's these advances in technology, advances in mathematics that allow us to discover all of the planets within our own solar system. By the middle of the 1800s, we've got this list that you're all pretty familiar with. Then not much happens for a while. Slide 4, fast forward to the 1980s. And at this point, science fiction has dreamed up fantastic worlds around other stars, but we don't know of any real exoplanets. Exoplanet being a planet around another star, entirely the realm of science fiction. Depending on how old you are, maybe this is before you were born, maybe it was after. In my case, when I was born, there were no exoplanets known. All of the planets we knew about were within our own solar system. And it wasn't until slide 5, the 1990s, that astronomers discovered the first exoplanets. And in many ways, this was the same kind of a sea change in our philosophy, our understanding of our place in the universe, as when we first realized in the 1600s that Earth was a planet as well, right? So first, Earth was the center of the universe, then we became a planet, then we realized our solar system is only one of many within the galaxy, with these first exoplanet discoveries only about 30 years ago. And so if we fast forward to today, on slide 6, astronomers, through various techniques, have discovered more than 4,000 planets around other stars and in our Milky Way galaxy. And based on the number that we've detected compared to the number that we've looked at, we can extrapolate and understand that, in fact, most stars within our galaxy have planets of their own. So now when you look up at the night sky, it takes on a whole new meaning. Those aren't just stars up there, those are planetary systems. The universe is teeming with planetary systems, and we just have to go out and discover them. So I'll take a couple minutes to talk to you about some of the exciting discoveries that astronomers have made about planets that are very different than the ones in our own solar system. So for example, on slide 7, over time, astronomers have discovered a few different classes of objects that we just hadn't expected. So the first is these hot Jupiters. These are things that are Jupiter mass, maybe even bigger, orbiting even closer to their stars than Mercury orbits to our sun. And these were the first planets to be discovered, not because they're the most common, but because they're the easiest to detect with the first detection methods that astronomers came up with. And I'll mention those in a couple slides. So right away, the first planets that we're detecting are already challenging our theories of how planetary systems form. Beyond that, there are these things called brown dwarfs. This is on the other end of the spectrum. Many of these things are orbiting far from their stars, although they can orbit closer as well. They're essentially souped up Jupiters. There's something in between a Jupiter and a star, about a dozen Jupiter masses all the way up to about 80. So they're not massive enough to burn hydrogen in their core and generate their own energy, but they're definitely too large to be a planet, and we don't think they formed in the same way as planets. Again, there's nothing like that in our own solar system, but astronomers are discovering these brown dwarfs in many solar systems. And lastly, one of the recent interesting discoveries, as astronomers have built up a census of the kinds of exoplanets, especially in the inner planetary systems, are that there's this kind of planet called either a super-Earth or a mini-Neptune, whose size is somewhere in between Earth and Neptune in our own solar system, and we're trying to figure out what those are. It turns out they're basically the most common kind of planet in interplanetary systems, but we don't have an example. So we don't have an example in our own solar system. So are they scaled up rocky planets? Are they scaled down gas giant planets? And maybe it's some of both. So one very active area of research within astronomy is trying to understand how many of these, how likely you are to produce a very large rocky planet, which could potentially be habitable, versus a scaled down Neptune, who's, with that thick gaseous envelope just wouldn't be habitable. How do you tell the difference between those kinds of planets with the measurements that we have? It's a really interesting and fascinating area of research that's at the forefront of astronomy right now. And lastly, one of the things I wanted to point out on slide 8 is that, at least for the moment, when you hear about new exoplanet detections, you're almost certainly going to be hearing about planets that are detected very close to their star. So this histogram here is showing the number of planets that are detected as a function of the separation from the star, and we're showing the separations of Mercury, Earth, and Mars for context. And you can see that the overwhelming majority of planets we know about today orbit much closer to their stars than even Mercury does. These hot Jupiters, these hot Neptunes, these hot super-Earths are baking next to their stars. Again, that doesn't actually mean that they're the most common type of planet. It just means that those are the ones that we can detect the most easily. So when you hear about those baking hot Jupiters most often in the news, just kind of keep in the back of your mind that you'll hear about them most because they're the easiest to detect. But of course, we want to learn about the whole diversity of planetary systems. We want to be able to detect planets at a wide variety of separations from their stars. And so we use a combination of a few different exoplanet detection techniques. On slide 9, I'll give a very quick overview. There's not enough time in this talk to dive deep into the details of every single one of them to begin with, but I can give you just a flavor, since you might have heard some of these terms before. So the most prolific method for finding exoplanets is the so-called transit technique. And that's where, if you have the alignment just right between yourself, the observer, and the planet, you might see the planet pass in front of the star, block a little bit of the star's light temporarily, and that little bit of a dimming in the star's light you can use to infer the presence of a planet. You might have heard of the Kepler mission or the TESS mission that have discovered literally thousands of these planets. And so it's the most prolific method of detecting planets, and it's the best at finding planets that are very close to their stars. So that's why there's this very strong bias to finding planets close to their stars. Another one of these indirect methods of detecting exoplanets is called the radial velocity technique. Essentially, when a planet and a star are orbiting, they orbit around their common center of mass, so the planet tugs just a little bit on the star while it's orbiting, and you can watch for the motion of this star over time to infer that there's a planet orbiting it. And again, this is best at detecting big things close to the star, although it can detect things farther away as well, given enough time. So this is one of the other prolific methods for finding exoplanets. The third one, and this is really going to come into its own in the next few years with some of the missions that NASA's working on, is called microlensing. And this is really kind of a fantastic technique that uses general relativity and the fact that things with mass bend space around them, and light beams are deflected by that bending. So you can actually see the effect of light bending around an exoplanet, around a distant star, to be able to determine that the planet is there. And lastly, and I should say that microlensing is especially good at finding things, sort of Earth separation, Mars separation from their stars. But it doesn't give you the detailed characterization information that you might want about those planets. So if you want to be able to study a planet in great detail, you have to take a picture. You have to look at the light coming from that planet. And direct imaging is a very powerful method for doing this. And I'll spend the rest of this talk focusing on direct imaging and some of the technologies that we use to take pictures of planets around other stars. It's exactly what it sounds like. And for the moment, it's very good at finding things quite far from their stars and very massive. We're working towards having it be able to see things closer to the stars. So on slide 10, start to give you an idea of the challenge of direct imaging of planets. Here's a beautiful Hubble image. You can see a bright star that's nearby in our own Milky Way, absolutely overwhelming all of these faint background stars and galaxies. Maybe buried somewhere under the glare of the star, there could be planets orbiting it that we want to image. And already just from looking at that picture, it seems like that might be pretty challenging to find a faint planet, but exactly how challenging is it? So on slide 11, the first challenge is that planets are, of course, faint, relative to stars anyway. Even the easiest case that we can do today is to look at these bright, hot, glowing young superjupiters. In these systems that are a few million or 10 million or 100 million years old, the planets are still warm from the heat of their formation and glow in the infrared. So compared to their host stars, those hot young superjupiters are about 1 million times fainter. And if you put that in terms you're a little more used to, at least I'm a little more used to, I can think of a lighthouse next to a firefly. Turns out that ratio is about 1 million to 1 as well. So already you're trying to see a firefly flying around a lighthouse. That's pretty challenging. Now, remember the fact that these are planetary systems that are light years away. So you need to be able to magnify and get very sharp images to see them. On slide 12, here's sort of an analogy. Imagine you put that firefly about 20 feet away from that lighthouse, and you're trying to see it from halfway across the country. That's the challenge. That's the easy ones. That's what we can do today. And in fact, on slide 13, we see an actual time-lapse series of images that were taken with the Keck telescope of 4 planets. If you're familiar with telephone numbers of the individual systems, the HR 8799 planets. And we've already blocked and then subtracted in data processing the glare of the star. So we're seeing these 4 planets orbiting around the central star. The little cartoon star is where the star is underneath. And these planets are all hot, young super Jupiters glowing in the infrared. This is a false color image. And again, you notice that these are very different than what's in our own solar system. They're orbiting at Neptune, Uranus, and beyond distances from their star, and they're much more massive than Jupiter. So challenging formation theories from the other side of the table. And these are, of course, very interesting planets. There's a lot to study about them, but on slide 14, where we want to go is to find solar system twins. We want to understand how common is our solar system, how do other planets compare to our own. So we have, we have these techniques that are very good at finding planets close to their stars. We have direct imaging that's very good at finding large planets far from their star. How do we improve direct imaging so that we can find things that are much more like our own solar system? And in particular, thinking about starting with finding something like our own Jupiter or our own Saturn. So on slide 15, let's work through the same brightness ratio numbers, but for Jupiter or for Earth. So remember how I'd said before, we were looking at young systems that were hot enough to glow in the infrared. Well, our own Jupiter and even our own Earth are really too cold to glow very brightly in the infrared. So instead, we need to go look at visible light reflected off of their cloud tops or off of their surfaces. So for something like Jupiter around a sun-like star, instead of 1,000,000 to 1 brightness ratio, we're talking about 1,000,000,000 to 1 brightness ratio. So instead of a firefly, it's a little cluster of bioluminescent algae. And if you go all the way down to something like an Earth, where we really want to be getting to with next generation missions in the coming decades, you need to be able to see a planet that's 10 billion times fainter than its star. And that really is basically like one cell of bioluminescent alga next to that lighthouse halfway across the country. So that's a factor of 10,000 better in brightness ratio than what we can do today. That's too much to do in one generation of instrument development. So we're going to do it in a couple steps. And the first step should get us to something like a Jupiter twin. And that's the mission that I'm a part of on slide 16, which is the Nancy Grace Roman Space Telescope. It was formerly called WFIRST, recently renamed after Nancy Grace Roman, who was the first administrator at NASA of the Space Astrophysics program. She was an incredible champion for the idea that space telescopes could revolutionize astronomy, could give us clear pictures above the atmosphere, could access wavelengths of light that don't pass through our own atmosphere. I'm sure many of you have looked at those astonishing images from Hubble. I remember when I was young and those first images were coming down, what an inspiration they were to me. Well, Hubble wouldn't have existed without Nancy Grace Roman. Her nickname's the mother of Hubble, and so I'm very excited to be on a mission named after her. And more specifically, I'm part of the team that's building the Coronagraph instrument on this mission that will prove out a few different key technologies to do this direct imaging. So on slide 17, let's sort of reorient ourselves. Remember that we're trying to uncover these faint planets from underneath the glare of the bright star. And now I've put it more or less to scale, what we can do on the ground there in that image on the right compared to the size scale from that Hubble image. And so the first thing that we'll need to do, of course, is suppress the starlight. And your intuition for how to do this is probably spot on. If you want to see an airplane flying next to the sun, your first instinct is probably to hold up your hand and block that light before it even reaches your eye. And that's exactly part of what we do in the Coronagraph instrument on slide 18. So the first thing we do is bring in this opaque dot that blocks most of the starlight before it reaches the camera. That is the coronagraph that the Coronagraph instrument is named for. And historically, it has that name because the first application of coronagraphs was actually to block the sun's light to study the corona of our own sun, but we can use it to block other starlight as well when we adapt the design. And after we put in the coronagraph, we'll also feed it through a series of specialized lenses and mirrors to do an even better job of suppressing that starlight so that by the end, we'll have very little starlight left over and we'll be able to still see the planets next to the star. So on slide 19, we'll go through a video that goes through this in a bit more detail. So the first thing you'll see is the overwhelming light from that star. We're trying to see planets nearby. So you'll see the light from the star pass into the instrument through a series of lenses and mirrors. The first thing we'll do is put in that occulting spot that blocks most of the starlight, and maybe you can just start to see the planet there. We'll use an advanced version of a coronagraph mask that has a few different parts to block the star. It's a little more sophisticated than just a black dot. And in the upper right, you'll see the image that we're trying to take of the planetary system. So it does an okay job of suppressing the starlight, but it doesn't get all of it. There's still some speckles left over. And that's because even the world's best lab can't fabricate a perfectly smooth mirror and a perfect lens. There are still tiny, tiny optical imperfections that scatter some of that starlight. So what we're doing in space for the first time with this instrument is being able to sense what those imperfections are and send commands to a flexible mirror, a deformable mirror, that will bend to compensate for those optical imperfections and help us suppress the rest of the light in the system so that then we can see those faint planets not overwhelmed anymore by the glare of the star. And so the purpose of the coronagraph instrument on the Roman mission is to prove out these key technologies for the future missions that will need to build upon that to image the Earth-like planets around nearby stars. And on slide 20, you'll see that it's real. We're starting to build it. We're going to be delivering this instrument in just over 2 years. So we're building those advanced coronagraph masks that block the starlight. You can see in the lower left and center that a couple examples of the kinds of masks that we're going to be installing in the coronagraph instrument. In the top middle, you can see our deformable mirror assembly. The square that you see on the left-hand side of the image is that flexible mirror itself. The rest is housing and electronics that drive it. In the lower right, there's a precision motor that will very precisely place all in a line all of those coronagraph masks so they do the best job of blocking the starlight. And in the upper right, there's something that I haven't talked about yet, which is our very sensitive camera. We're using what's called an electron multiplying CCD, but essentially what it means is that it's a detector that can actually count individual photons as they come in. The planets that we might be looking at are so faint that we might only receive one photon from them every couple seconds. So every photon is precious. We have to be able to collect it and measure it. We can't have it buried under the noise of a traditional camera. You've probably encountered similar struggles even with your smartphone trying to take an image at night. It just gets very, very noisy. And so that's because the camera itself has some measurement noise every time it takes a picture. And what's special about this camera is that it can multiply the signal from the photon before above that read noise. And on slide 21, I've given a very fast overview of the coronagraph instrument, but that's only part of what we'll do with it. And that's only one instrument on the entire Roman mission. So there are a number of places you can go if you want to find out more about the Roman mission. I'd especially refer you to the Roman Virtual Lecture Series. There are scientists and engineers from the project who talk about the variety of different science applications that Roman will tackle with both the coronagraph instrument and its other instrument called the wide field instrument. The wide field instrument will detect exoplanets with that microlensing technique that I alluded to before. And it will be capable of doing lots of other science, studying our galaxy, studying other galaxies, looking for dark matter and dark energy. And there's some really great lectures there about those science topics. And if you want to dig a bit deeper into the specifics of the instrument design or the mission design, the Goddard website, the JPL website, the IPAC website all have instrument parameters and more resources for you to read about. And so on slide 22, we start thinking forward, right? If the purpose of the Coronagraph instrument is to prove out these technologies, we're doing that for a reason. We're doing that for these future mission concepts. So NASA is in the process right now, over the next few months, they'll be finalizing a decision about what will be the next major mission after James Webb, after Roman. What will astronomy do as its next grand mission? So two of the concepts that have been submitted to the competition are the HabEx and LUVOIR concept, and both of these include instruments that would be able to image and take spectra of an Earth analog, a true Earth twin around a nearby sun-like star, and they would build on the technologies that we're demonstrating with the Roman Coronagraph instrument. So if one of these is selected, we could really be thinking about taking that first image of an Earth-like planet around a sun-like star in maybe 15 to 20 years, which is really exciting for me. I would sure love to be involved in a mission like that. And so I'll close on slide 23 with this iconic image that I think many of you may have seen before of Voyager staring back at Earth, that pale blue dot in the distance. And of course, that's within our own solar system, but we're getting close to the point where we can really think about taking the pale blue dot image of an Earth-like planet around a nearby star, finding that Earth twin in the future. And I'm very inspired to think about how we've come in just about 30 years from knowing about no planets other than those in our own solar system to finding thousands, to being on a path to finding one like Earth. And with that, I'll close and take questions.
Wow, thanks so much. I feel like the common thread in between the last few videos that we've done is just the excitement and kind of just the optimism on hearing the pace at which technology is moving forward. I think it's just incredible that in our lifetimes we've gotten so far. So we have so many questions to kind of get through here. I don't even know where to start. One that I've always wondered is, you mentioned a little bit about the kind of the sampling error problem, right? That these hot Jupiters are so easy to find. Did astronomers kind of have a notion as they were detecting these that sampling error existed? Did they know that there had to be something smaller out there, or was there a little bit more surprise as technology got better?
Oh yeah, that's a really important question, is how well do you understand your sample bias when you're designing an experiment? So in fact, probably we had the technology to discover exoplanets before the 1990s. The radial velocity technology was there, but people didn't expect there to be super Jupiters in orbits smaller than Mercury, so they didn't look. We could have found them earlier, but we just didn't think to try, right? I mean, that's a bit of an oversimplification, but not much. So once people started discovering those, they did understand that there were biases in the detection methods. They understand if what you're looking for, say in radial velocity, you're looking to observe the star appear to go in a circular motion for at least a couple of orbits, so you know that you've truly observed a planet orbiting that star. Well, of course, the planet's year is much shorter if it's close to the star, as opposed to very far away from the star. It's a slow, stately motion. And that's a known bias, so you're more able to detect things on short periods, and you can correct for that in your results. The same thing's true with transits. And so, in fact, when we were talking about the knowing from 4,000 exoplanets that every star in the sky pretty much is going to have a planetary system, that's taking how many planets have been detected with the transit method, correcting for that bias, the fact that we know we're most sensitive to planets near to their stars. We have some idea of if you have a planet in the inner star system, how many planets might you have farther out based on predictions from planet formation, making all of those corrections, and then that lets you come up with the prediction that basically all stars have planets.
Gotcha. But of course, the 4,000 some that are confirmed, these are ones that we know for a fact. They haven't been part of that extrapolation.
Yes, that's right.
A lot of questions coming in. Of course, everyone has to wonder this at some point. When we talk about these thousands of exoplanets and beyond, how is the nomenclature determined? What is this naming system that is so confusing?
Oh yeah, the telephone numbers, right? So let's pick probably my own personal favorite example, which is HD 106906b. So what that means is that the planet is orbiting the star HD 106906. So that's the HD is the catalog, Henry Draper catalog. It's a catalog of a bunch of bright stars, and it's the 106,906th bright star in that catalog. You'd have to look up in the catalog to figure out where it is in the sky, but it's just a catalog name that we give to that particular star. In fact, there are multiple bright star catalogs, so it might also have an HIP number or an HR number, but usually we just choose the most common one, the HD numbers, to designate these. Then in nomenclature terms, HD 106906A, that's the star. That's the star itself. It's just we usually leave the A off because it's redundant. We know we're talking about the star usually. So then every additional object in the system gets the next letter in the alphabet. So HD 106906b means it's the first planet. It's lowercase, so it means it's a planet. Uppercase would be a star. It's the first planet discovered around the star HD 106906b. If there were others discovered, they get C, D, E, F, and it doesn't matter how far they are from the star. Let's say there were three. If you discovered the middle one first, and then the outer one, and then the inner one, they would be C, A, B if you went out in radius. So the letter doesn't necessarily tell you which one's closest. It tells you which one was discovered and confirmed first. So you have to look that up in the catalog as well.
Wow, so you really have to hope you find them in the right order, or it gets even more confusing.
Exactly.
So then it's someone looking at our solar system from afar would say that Mercury, Venus, Earth, Mars are lowercase a, B, C, D.
Yeah, exactly. Probably they would discover Jupiter first because it's the biggest and the brightest. So and Mercury might be last because it's quite small and faint and near. So you might end up with a weird alphabet soup.
Speaking of the presence again of these super Jupiters that kind of are out of place, if you will, how do they get there? Is there some sort of migration? I mean, do they keep the gases that they hold?
Yeah, well, I mean, to be honest, that's still an area of active research. There are a couple different paths that astronomers think these planets could take. So one of them is migration, just as you say, in the process of formation. So planets form within a disk of gas and dust, and I think I've got a little cartoon of it on slide 27. So you have this big initial gas cloud that collapses down under its own gravitational force. That little bit of angular momentum that might be there, as it collapses down, it spins out into a disk, sort of like when an ice skater brings in their arms, they spin faster and faster. So that's why we get the little disk of material around the forming star. Within that disk is where the planets will form over time. And so something big and massive like a Jupiter, you might start out by actually building up a core, like pebble by pebble, until you have sort of a rocky core that gets massive enough to grab on and hold its atmosphere of hydrogen and helium gas. And as it's pulling in that material, it can clear out a gap in that disk. And you can kind of see in the cartoon there, the gap being cleared out in that disk. And this gap clearing process, in some cases, can cause the planet to migrate towards the star. So one option for some of these planets is that they migrate during their formation process. We don't think that can explain all of them. So the other option that may be forming some of these is to have kind of close collision events. So the planet formation process can actually be kind of violent. You're forming these cores first by pebbles, then boulders, then massive rocks collapsing and hitting each other in that disk. Well, you're forming lots of planetesimals at that point, lots of planets. If they get too close to each other, they can almost collide and can dramatically change their orbits. So if you had a Jupiter that very nearly collided with another one, what could happen is that the outer one might get scattered out of the planetary system and the other one might get scattered in much closer. So there's a couple different options for how that might occur. If you migrate in close enough, to your question about the atmospheres, if you're close enough to the star, yes, you can evaporate that hydrogen and helium off of the planet. So one of the other options for these super Earths that people are talking about is, could any of them maybe be the leftover remnant cores of a giant Jupiter-like planet that lost its atmosphere because it was so close to the star? That wouldn't explain super Earths that are farther away and too cold to be evaporated off, but maybe some of these could also have formed by that pathway. There's a lot of what ifs, and we're trying to figure out a more definitive way to know the history of any individual one.
Yeah, that's really exciting. I think my brain just clicked that now I can tell all my students and my physics students when they ask me about why we need to learn angular momentum and inertia. Now I can tell them, if you want to go find some super Jupiters, this is how you're gonna do it.
Exactly, and you got to be careful, because that's how we got the moon, right? Is a big planetary collision, and conserving that momentum meant that we ended up with our moon spinning around our Earth. So collisions have dramatic effects and on planetary habitability in the course of our history.
Yeah, and the other thing you mentioned is, kind of the idea of an atmosphere evaporating ties in really well to another question, which is, haven't there been examples of us being able to detect exoplanet atmospheres as well?
Yes, absolutely. So what we have not been able to detect an atmosphere on a truly Earth-like planet, and not one that we know is habitable. We haven't seen so-called biosignatures that would ensure that we know that it's inhabited, but we have definitely, we being astronomers, astronomers have definitely observed and characterized the atmospheres of a number of different planets. So on the direct imaging side of things, the planets very far from their host stars, in those bright glowing infrared images, that's light being emitted off the top of the atmosphere of those giant planets. We can put that through a spectrograph. We can measure the relative composition. For those gas giant planets, we see a lot of hydrogen and helium and water and methane. Also, they're so hot that you get like molten rock clouds. So you see silicates and iron clouds on these very hot planets, pretty inhospitable. And on the side of the planets that are the kind of planets that are very close to their stars, those ones that transit their star, so remember, pass between the star and you as the observer, a little bit of that starlight can skim through the atmosphere of those planets. And so when the starlight passes through the gases of the atmosphere of that planet, depending on the composition, certain wavelengths will be absorbed from the light as it passes through. And so through that absorption spectrum, we can measure the composition of the atmosphere of some transiting planets. You need to have a transiting planet around a pretty bright star. It needs to be a pretty big planet relative to the star in order to get a big enough signal. But that's the other way in which astronomers have been measuring the composition of planets so far.
I love it. Chemistry and physics. I'm sold. I got my money's worth today. I have two more questions for you. Just talking a little bit about transits. Will the Roman telescope have any of the same kind of complications in looking at certain stars when there's, like, for example, a sunspot or a flare or something like that? Does that convolute the data at all?
Oh, yeah. So yes and no. So first, the no part. For the coronagraph instrument, for the direct imaging instrument, we're blocking all the light of the star. We don't care whether it has star spots or a flare. That just changes the overall brightness, but we've suppressed that, and we don't really care that much about the instantaneous brightness of the star. We're not looking for transits with the coronagraph instrument while we're also trying to directly image those planets farther from the star. But the wide field instrument will be doing an exoplanet search. Primarily, its survey is designed to enable the microlensing detection technique, but that data, the way they take the data is to look at several 100,000 stars at once and take frequent images to look for changes in brightness. That lets you do the microlensing technique. That also lets you do the transit technique. And so just like with Kepler or TESS or any other transiting exoplanet mission, you do have to worry about star spots masquerading as planets. And there are ways that astronomers can disentangle star spots from planets, maybe by looking at different wavelengths, by looking at how repeatable those dips in brightness are. But it can be pretty challenging, especially for cases where the rotation period of the star is maybe close to the orbital period of the planet. How do you tell what was the planet and what was the star? So it's definitely a case of false positives, and people will be having to use those same techniques for differentiating the two with the Roman data as well.
Awesome. Well, last question for you. A little bit tough if you can do your best to explain for us.
All right.
What is it that this kind of flexible material that's being used for the Roman telescope, and how is it controlled?
Oh yeah, that's really neat. So it doesn't have to move very much. The motion that was shown in that video was really exaggerated so that you could actually see it. The imperfections in the optical system are nanometer scales, 10 to the minus 9 meters that we're trying to correct. So we need incredibly precise actuators. So actuators are the grid of little pins behind that thin sheet of reflective material that move and bend it. They're made of, I want to say, lead, magnesium niobate, something like that. I should remember the material. But the point being that as you change the electrical current to those actuators, they move very repeatably, very precisely, by very small amounts. And so we have a grid of about 2,000 by 2,000 of those actuators to very finely control the shape of that mirror. We don't have to do it very fast, right? Because you're just correcting for optical imperfections in the system and the sort of changes in the optical alignment that might occur over time. So, let's say Roman points from one star to another, the sun is hitting the telescope a little bit differently, heating a little bit differently. Things might move and shift relative to each other just a little bit over the timescales of a few hours, and we have to be able to correct for those as well. I'll just sort of a side tangent. This is actually very similar technology-wise to what's done on the ground with adaptive optics. So to create those images of the planetary system that I showed you from the Keck telescope, you have to be able to correct for the blurring effects of the atmosphere. I don't know if I have just 1 minute to show a cool video or 20 seconds, but on slide 26, there's a high-speed video showing this in action, where basically you'll see, this is a ground-based image of a multiple star system. So not planets, but multiple stars. First, you'll see when you look up at night and the stars twinkle, that's actually because the atmosphere is blurring the light as it passes through. And so we have to correct for that to be able to compress the light of the star and to remove that scattered light. And so in this little video, it shows you turning on that adaptive optic system from the giant fuzz ball of twinkled starlight to the three stars in that system. And it uses a very similar deformable mirror technology, but it runs really fast, like 1,000 times a second, because the atmosphere is moving and fluctuating that quickly. What's different and why we have to go to space is that, we just cannot move those deformable mirrors, do those calculations fast enough to correct for enough of the atmospheric distortions to see the things at the 1,000,000,000-to-1 contrast ratio. So the only way to get to the really faint things, the Jupiter twins, the Earth twins, is to just not have to deal with the atmosphere at all, and that's why we're going to space.
Awesome. Wow. Yeah, thank you so much. I mean, this talk really had it all. I love seeing how multiple sciences come together in this kind of interdisciplinary way. So it was really, really exciting to learn some things with you.
Yeah, thanks for having me.
Yeah, so thank you so much. Just to kind of close out, guys, I'll show you just a few slides from our office and the Office of Education. On my first slide here, you'll see the website that I hope you guys will go check out, where you can see so many more activities and some information on exactly this type of material. We have so many cool lessons on exoplanets. For example, on my second slide, you'll see an activity that we call Habitable Hunt. This is based around looking at how far those potential exoplanets could be from their sun and how we detect that using mathematics. And on slide 3, you'll see, in fact, some of my favorite stuff, looking at the chemistry and geology on what are these planets made out of, and how do we determine that? How can we kind of model what that terrain could be, and as we learned, how we could potentially see it in the atmosphere. On slide 4, you'll see a general website on exoplanets, exoplanets.nasa.gov, an incredible resource with tons of videos, multimedia, pictures, and the kind of running count on how we're doing as we're exploring the universe. On slide 5, I kind of want to point you guys to the news section of the education website, because this is where you'll find our kind of continuing coverage as new articles come out, written to you as either a student or a layman, as you kind of delve into this and learn a little bit more on your own time. But if you're a teacher, on slide 6, you'll see our education activities based around standards and grade level. So very, very easy to navigate as you kind of find the activities that are written for your students, and you can get there quickly. In the time of virtual learning, on slide 7, if you're still remote or you're looking for just a project to run on your own, the Learn section is a really, really great place for kind of student-driven activities. This will be kind of run step by step with photos and allow you to kind of do all of this at home. Just if you're a geek for astronomy like I am, this is how you can kind of explore it with just kitchen-type materials. On slide 8, you'll see kind of how we've put some of this material into modules so that you guys can, really just get lost, right? Just dig deeper in all of these facets, whether it's activities, videos, just FAQs for families. And of course, I'd be remiss if I didn't point out on slide 9 that we have educator-focused workshops once a month, the Saturday following these talks. So come out and, practice some of these, learn more, as we'll model some of these activities that I highlighted today, based and rooted on the research that we were just discussing. So really a ton of great opportunities to take all of this really fascinating science that kids are thrilled about and put it in their hands and put it into your classrooms and get to inspire the next generation of awesome astronomers. So with that, I'll close us out. I'll thank you guys so much for joining. And of course, absolutely, we're so lucky to have our amazing speaker. A very, very exciting time for astronomy. So much left to explore. Our universe is a big, big place. So there's no shortage of cool science to go do in it. So thank you guys so much for joining us, and I hope to see you again soon.